This is what I would call one of those big idea talks that we're not going to really dive a lot into the implementation details and the technical details, but do reach out to me because I've got a lot more material that dives a lot deeper into how to actually make this happen. But it's a space that I've been following for many, many years. And I knew it was big and I knew there was potential, but it wasn't until I was working on a project a couple of years ago for one of my clients that I saw what these ideas and what this technology was truly capable of. And now I'm starting to see it everywhere. So all of this really helped me finally connect the dots. And these are technologies that are not only enabling enterprise innovation, but going back to Neil's very inspiring keynote this morning, these are technologies that people are using to fundamentally change the world for the better. And we're seeing this in social media. These technologies are enabling entirely new models of social media where you own your data and you own your community. And it's about community. It's not about advertising. It's not about algorithms. It's about connecting with people like we used to in the early days of social media. We're seeing it changing us away from the surveillance economy where every company that we interact with today is hoarding all of our data. These technologies are allowing us to flip the script where we own our data, we control our data, and we get to choose who and what we allow. Who we allow to touch that data and what we allow them to see. And it's ours and we can keep it and we can move it. There's really, really incredible stuff happening in this space. The customary introductions, of course, if you've seen me before, you'll know this. I live somewhere in the intersection of magic and technology. And if there's one talk that more and more I feel like also exists in that intersection, one topic, it's this one here. And the thing is, as exciting as all of this is, these ideas aren't new. And a lot of these ideas have existed in some form or another for 20 or 30, sometimes 40 years. I actually have a talk where I go all the way back to ancient Greece and talk about the developments that brought us to the enterprise knowledge graph. And when you look at these technologies, really there's two ways to look at it. You can see it as either as a huge opportunity or an existential threat because these ideas are beginning to disrupt how we think about and build software. So there's a lot of things, there's a lot of reasons it's worth exploring this space. And I want to tell you a little bit about the story behind this. And to do that, I want to start with how I got here. And the way I got here, very simply, was luck. I got lucky. In fact, I've been extraordinarily lucky only 3 times in my life. These are 3 events that shaped the course of my entire life, and I could never have foreseen the consequences of these tiny things. The first one is in the 1980s. This is where I grew up. This is the library in the town that I grew up in the Sweetwater County Library. And growing up, my parents, we didn't have much, but my parents always wanted there to be books in the house. They wanted us to be literate. They wanted us to read and love to read, and we would read together. We would go to the library a lot, and every year we would go to the library discard sale. Because every year the library would go through their books and say, well, we need to make room for the new books, so I guess these ones are going to go. But they didn't want to just throw them away and shred them and pulp them. They wanted them to go to a new home, so they would sell these books fairly cheap. But we wouldn't go on the first day or the second day or the third day. We would go on the last day of the discard sale because we didn't have any money. On the last day, they would give you a giant bag of books, or a giant paper bag. And for $1, you could have that bag, and as many books as you can stuff in that bag, those were yours. And so my mother would give me $1, give my sister $1, and off we'd go. And I'd wander around and grab various titles. And as I was browsing the shelves and the tables, I saw this book, George B. Anderson's Magic Digest. And I saw the kid there putting on a show and these amazing posters. That's where I first learned about PC SOCAR. And I thought, why not? And I grabbed that book. It was one of dozens of books that I put in that bag. But that book, which cost me pennies, changed my entire life. It launched a journey that put me on film, TV, and radio, took me around the world. In my life, this couple of pennies I paid for this book gave me a return on investment of over $1 million in lifetime performance fees. This book also birthed my career as a software engineer, and in a very real sense, this book is the reason that I am here today with you. And it changed my life. The second time I got lucky was in the late 1990s. I was going to the magic shop, as it happens, in London. And on that day, I was on a bus, and the bus turned a corner, and I lost my balance, and I fell in the lap of this beautiful woman. And we started talking and hit it off, and she was beautiful, charming, and devastatingly intelligent. And I forgot about the magic shop. I didn't go to the magic shop that day. I followed her. We went to the museums and toured around London and had a really amazing day together. It's a day I'll never forget. It was a shame that she and I lost touch about 5 years after that incident. We stayed in touch for about 5 years and then lost touch. Although we did reconnect 20 years later, we got married. You saw her here earlier today. This is one of our wedding photos in New Orleans, Louisiana. And again, I lost my balance on a bus going to the magic shop because of that book, changed the course of my entire life. But the third lucky thing is I had the insane fortune to grow up in this house, in this town, in this state. Now, this is the state of Wyoming, a very sparsely populated state. It's not very well known. It's not very popular. There's not a lot of people there. In fact, in the United States, I talk about this when people say, what's so lucky about the state of Wyoming? And to be fair, there are things I'm sure to love about the state, but to outsiders and this insider, they can be hard to spot. In fact, one of the few times this state has even been mentioned on TV was when the comedian John Oliver had this to say.
Think about that. Over 500,000 votes were rejected in the primaries. That's practically an entire Wyoming disappearing into thin air. That is really bad. Well, that's because of the actual Wyoming disappearing, in which case the real market is the best. It's a semi-arid sandbox filled with fluffy cows and nothing. The most famous part of Wyoming is the state trying to swallow itself up. And the second most famous part is it spitting itself out again. It's clear that even you don't like New Wyoming, and it's getting hard for the rest of us to watch. And
all of those statements are accurate, by the way. And it's a little bit unkind, but I can say as a former Wyoming resident that we're mostly just grateful to have been noticed. But in that semi-arid sandbox filled with fluffy cows and nothing, something was happening. And that something was the National School Network test bed. You see, in the 1960s and 70s, we created this network called ARPANET. And that became the NSFNet in the 1980s. It got given to the National Science Foundation, and it was connecting universities and research institutions. And a couple of visionary people said, what if we connected the NSFNet, this is before it was the internet, the NSFNet, to regular schools? And so Green River was the pilot site. It was the foundation of this project. This is Jim Rogers talking about this and what this could possibly mean. So in America, I lived in the very first school district in the country to be connected to the internet. And this guy, Jim Rogers, was one of the visionaries behind it. And if you're anything like me, you might be thinking, wait, this town in the middle of nowhere, an oasis of 8,000 people in the middle of a high desert wasteland? This town, which is largely just a lingering vestige of the Transcontinental Railroad? This town where the infinitely inflappable Phileas Fogg stopped briefly on his 80-day journey around the world. And throughout the entire novel, Fogg retained his implacable calm, but just 5 minutes in Green River, he was ready to kill someone. Yes, this town. The citizens for Green River, Wyoming were all present for the dawn of the information age, the change into the post-postmodern, the meta-modern age. And the visionary behind it, this guy, just happened to live here He was my next door neighbor. He was my mentor as I was learning to program, as I was exploring technology. He was a really influential force in my life. And as a result, I've had a front row seat to the revolution that is the World Wide Web. And you now have a front row seat to the next revolution. And I say this, and it sounds a little bit incredible. And not the, wow, that sounds incredible. It's like, no, I don't think this is credulous. And maybe I'm overselling it. So let's look at the first revolution for a moment. You know, bit by bit, we started connecting computers together. We standardized on TCP/IP in 1983, 1986 with the NSFNet, 1989, Tim Berners-Lee wrote a proposal for a global standards-based hypertext system. So in 1989, we are on the brink of having access to untold amounts of information. And that meant that if you were conducting an experiment at CERN in Switzerland, you could benefit from the results of simultaneous research happening on the other side of the planet instantly. The problem was, who is doing what research? Where is it taking place? When was it added? How do you access it? And at that time, the dominant application protocol was Telnet, which means you would connect in sort of a virtual terminal over the network to a machine, and every single one of these machines and the applications and the information systems was different. So you'd have to learn all the commands and quirks, all the different ways to search for what's in there. They are all organized differently, and as you dig around and explore this system, oh, you didn't find what you're looking for. Well, now you got to connect to a different one. Well, that was a VAX, and this is a PDP, so you got to start all over again. Read the documentation. Learn an entirely new system over and over and over again. And Tim Berners-Lee said, well, why does it have to be that way? What if we just agreed on a simple set of standards? And this is the infamous World Wide Web proposal. In fact, this is the very copy that Tim Berners-Lee gave to his boss in 1989. And in 1989, his boss took it, and he heard nothing for a year or so. And in fact, it wasn't until Tim Berners-Lee's boss passed away and they were going through his belongings and they found his papers that they found this copy of this document. When he read it, he wrote on the top, vague, but exciting. And maybe what I'm talking about right now is going to be vague, but it is exciting. So Tim Berners-Lee saw that there was a problem that needed a solution. He said the problem of information loss may be particularly acute at CERN, but in this case, as in certain others, CERN is a model and miniature of the rest of the world in a few years' time. CERN meets now some new problems the rest of the world will have to face soon. And maybe in 10 years, there might be commercial solutions to the problems above, but today we need something now. And there was, the problem was there was so much valuable information, it was just out of reach, and it was a problem that wasn't going away. And so in the early 1990s, they got a Next computer, and Tim Berners-Lee's boss said, hey, you wanted to work on that mesh of information system, and you wanted to play with this object-oriented programming thing. Well, here's a Next computer. Why don't you play with both? On your own time, of course. We're not paying you for this. And he did, because he was passionate about it. He wanted to work on something that mattered to the world, like Neil talked about. And in 1993, we had the dawn of the web, the first web servers. In 1993, by the end of 1993, there were just 50 web servers. By 1995, we already had giants like Yahoo and eBay and Amazon. Today, of course, we have self-driving cars. We have light bulbs that obey our commands. We have continuous revolutions in science and technology. We have access to the sum total of all human knowledge in our pockets. And we're connected to all of this constantly on this ubiquitous 5G network. And, I put this slide in here as a joke about what the future might be, but we literally have robots that clean up after us now. How did we come so far so fast? Information made it possible. Access to that information. Imagine you're a programmer and you run into some kind of gnarly error message, gnarly stack trace. What do? Do you start parsing all of this? Do you start disassembling the sources so you could walk that stack? No. We ask the entire planet. We just ask everybody in the world. I just took this a random question from Stack Overflow. And in this case, it was a developer in Pittsburgh, Pennsylvania in America, ran into this issue, asked the entire planet, and less than an hour later, a Google developer expert in Paris answered. And now we can get the answer in minutes, we can get the answer in seconds. Now, I learned to program here on an Apple II computer. We didn't have the World Wide Web. We didn't have Stack Overflow. And, if I had a problem, I had to figure it out. I had a book or two. I could ask my neighbor, but that was it. And it's really easy to romanticize this time and talk about this like, oh, yeah, back in my day when programmers were real programmers. And, yeah, there was a time when it was that hard. And we are grateful for the giants whose shoulders we get to stand on top of. Because there was a time when there was nobody to ask. I love this quote from Admiral Grace Hopper when she was interviewed by David Letterman. And he says, how did you know so much about computers back then? And she said, we didn't. It was the first one. And as a result, sometimes we get the occasional imposter syndrome. Like, do I really know what I'm doing, or do I really just know how to use Google? Does it matter? Because, a quick answer changes everything. I look at the comments in Stack Overflow over and over again. You saved me weeks of toil. You saved me days of search. You saved me days of work. You saved me weeks of stressful aggregation. You saved me weeks of struggle. You saved me days of headaches. You saved me days. You saved me months. We see this over and over again, and it's true. I remember when it took days and weeks and months to solve a problem, and now we get the answer in seconds. So let's do some back-of-the-napkin math. Here are some stats from Stack Overflow from a while back. Stack Overflow has been around for about 10 or so years. And it says on average they get 262.1 million monthly visits. It wasn't always that high. So let's fudge the rest of the numbers to kind of make the math all work out. Let's assume only 40% of the visits at Stack Overflow, somebody gets an answer. And let's assume instead of weeks or months or days, let's just say it saves 4 hours. So 40% of the visits Stack Overflow results in people staying 4 hours, only 4 hours, not weeks, not days, not months. That means that that's 12.5 billion questions answered, 50.3 billion hours saved. In real terms, that's 5.74 billion or million developer years. That's 5.7 million developer years of doing this instead of doing this. And what made this possible? Very simply, information. Sir Tim Berners-Lee so masterfully solved the problems of access to information with this mesh that he imagined that we don't even think about it. And all of the complexity gets abstracted away by a simple set of standards. Think about it. If you're accessing a website, do you ever think about what kind of machine that's serving that information? No, it doesn't matter. Where's the computer located? That doesn't matter. Well, what kind of operating system is it using? It doesn't matter. What operating system am I using? I could be on Chrome OS or Linux or Mac OS or Windows or whatever. It doesn't matter. What browser am I using? I could be Brave or Firefox or Chrome or Edge or any of these or Arc. It doesn't matter. What software is serving the information? Is it WebSphere? Is it Nginx? Is it IIS? Is it Apache? Is it Node? It doesn't matter. Where's the information stored? Is it files? Is it in a database? What kind of data? Is it an XML database? Is it a relational database? A document database? It doesn't matter. How old is the software on the server? It doesn't matter. The original web server and the original website is still online and it still works. And not only that, because I was bored one day, I got NCSA Mosaic, the very first public web browser running on my computer. And it was actually really easy because other people have done the hard work for me, as is often the case, and we could stand on the shoulders of those giants. And that browser still works, and the original web server still works. And if there's something I want to learn more about in that information, I don't have to come out and come in a different direction. I just follow my nose. I follow the links, and I can explore this vast global space of information. It's simple, it's scalable, it's effortless. In other words, it just works. And we've gotten so used to having this limitless information available to us at our fingertips 24/7, 365 days a year, that it's worth taking a step back to appreciate how truly awe-inspiring this achievement really is. But here's the thing. This vague but exciting proposal took a couple of years for anybody to pay attention to it. Like, we know in hindsight how important this was. But at the time, most of the people who saw this said, so what? And that was an era where a directory of people on the internet was the size of a phone book. Back in those days, back in the 1980s, this is a book that had details of every machine and every person on the internet. Can you imagine that today? It might as well just be the planet. It might as well just be the web. And so if you're wondering why what I'm talking about today is so important that most people have never even heard of it, well, it takes time for an idea to reach its tipping point. And so like I said, when Tim Berners-Lee presented this proposal, the reaction was mostly, so what? But the penny dropped. And the penny's about to drop on linked data. And it also takes time for these ideas to gain momentum. And Tim Berners-Lee saw this. He said the result should be sufficiently attractive that information contained would grow past a critical threshold. That's the key, the tipping point. So that its usefulness to the scheme would in turn encourage increased use. What he's describing here is network effects. This is when something reaches the tipping point. If I created a new social media site today, would you join? No, probably not. Because, I mean, I'm there, but about everybody else you know? And it's just like, I don't know if I want to join a social media site just to talk to Mike. But there was a point where we were like, oh, there's nobody on Facebook. There's nobody on Facebook. Oh, everybody's on Facebook. I need to be on Facebook. And there was a time when nobody's on MySpace. Nobody's on MySpace. Oh, everybody's on MySpace. I need to join. And then, oh, nobody's on MySpace. I need to leave. Like, this is what network effects do. The utility of the network is proportionate to the number of nodes, and it's exponentially proportionate. And this is why we see this kind of growth. So here's the crazy thing. As powerful and as revolutionary as the web was and continues to be, what we have today is just a sliver, a fraction of the vision. It was always supposed to be more than just linking documents. So this is Aldo Bucci's or Bucci's graphic here, talking about these evolutions. And in the beginning, in the 1960s, we had computers, and they were all isolated. And then when we had an enabling standard, we started to be able to network these computers. And then we had documents and media that were siloed. And then we had another enabling standard, HTTP, and we started really linking these computers. We really started linking these documents. And as we're doing this, as we network them, the physical location becomes irrelevant. The containing file system becomes irrelevant. And over time, we can move up this projection all the way into this web of data where the databases and the applications become irrelevant. And we have a space of data with everything that goes with it that we can explore the same way that we can explore the web of documents. And we're on the way to reaching the tipping point of this next phase of the evolution. We're mostly here, but we can move here. And everything we need to make this happen is in place and people are doing it. And it's just a case of reaching that tipping point. And Tim Berners-Lee talked about this. And he even said, you know what, this is cool, but it'd be even cooler if we started linking the databases together as well, the same way we link the documents. And we never really did that. And even though nobody else really did that, Tim Berners-Lee and the merrymakers at the World Wide Web Consortium, they never stopped. And one of the ideas was the web succeeded because it wasn't centralized, right? We never had to put resources into the web. We put the web into our resources. And we can do the same thing with our data. So if we want to integrate all this data, this seems like a big challenge. If we want to integrate all the data in the world or all the data in our enterprise, well, how do we do that? Because data comes in many forms, many shapes, many serializations. In fact, there are 4 heterogeneity problems that we have to solve. So we need to be able to connect the data wherever it is, however it's stored. Just like we put the web into our resources rather than put our resources in the web, we can do the same thing with our data, where it is today, whether it's an Oracle database or a MySQL database or a MongoDB or anything else. We can do this. So in 1997, the W3C, the World Wide Web Consortium, first published a public draft specification of a standard designed to build, quote, a vendor-neutral and operating system-independent system of metadata. And it solved the 4 heterogeneity problems. There's 4. There's syntactic heterogeneity, there's structural heterogeneity, semantic heterogeneity, and identity heterogeneity. In other words, is the data we want to integrate in the same format? Is the data we want to integrate, are they incompatible shapes? And anybody who's ever tried to put a graph or a jagged hierarchy into a relational table knows that these are not always compatible shapes. There's semantic heterogeneity. In other words, when I have a term to describe something and you have a term to describe something, do we mean the same thing? Do these terms have the same implied behaviors? There was a big problem in 2020 as we were trying to integrate all of the data from COVID cases, because some people were saying, oh, here's our case count for this date. And other people were saying, here's our case count for this date. But when one group said case count and another group said case count, they were talking about different things. And so we need some way of being explicit with the semantics of our terms. And identity heterogeneity. You know, if you say, oh, did you see Michael's talk? And you say, I saw Mike's keynote. Are you talking about the same person? Maybe. Because Michael and Mike are, you know, you can do that. I have a friend named Ashish, and sometimes he goes by Ash. Same person, different identifiers. But that's not always useful because, does anybody else know an Ashish? Yeah, okay, some hands. Yeah. You think it's the same Ashish I know? Probably not. It's possible, but probably not. And in the US, Michael is one of the most common, has been one of the most common names for baby boys for about 50 straight years running. And so there's a lot of Michaels. There's a lot of Venkats. You know, there's a lot of people with the last name Gandhi. It's so how do we guarantee that we're talking about the same person, even if we use different identifiers, even if we use different labels, even if we use different names? And we've solved all of this. But to do it, it starts with having a flexible data model. And the web worked because we could take our data, our information, wherever it was, and project it into HTML. Well, it turns out we could do the same thing. We can project our data into a specific format because it exists in a lot of formats like this. Now, one thing we can do if we want a general data model, in fact, if I just survey developers, and we've got tables, we've got graphs, we've got JSON documents. Well, what's the lowest common denominator to represent all of this? Name-value pairs. We can just create name-value pairs. And maybe it looks something like this, because JSON is really just decontextualized name-value pairs that are grouped together into, you know, arrays and objects and things like that. And we still have problems. What is 6995? It might mean something to me in the context of my person table in my HR database, but it doesn't mean anything to anybody else in the world. And if you have this 6995, how do you even find out about it? You have to know. You have to read the documentation or read the source code, or somebody has to tell you. Well, what if we take the same scheme of identifiers that we've been using so effectively for the last 30 years that we don't even think about them, and we use a uniform resource identifier? So this person now is a resource, and we identify it with the URI, example.com/people/id/6995. Well, now we know, even though every single one of us, if we have any database table with monotonically increasing like identifiers for the primary key, we all have 6995 keys in our database. But I own example.com as my namespace, and I can partition that namespace into people and subpartition it by ID, and now I have an identifier that is globally unique. It is namespaced. I control it, and I can mint any identifiers I want, and we will never have a collision because I'll use my namespace, you'll use your namespace, and we can always say, oh, this identifier and that identifier, they mean the same thing. And that means anything that's true of this is true of that. And also, now you have that. So you don't know what that 6995 is. What do? You follow the link and see what you get. And then in that, you get more links, and you can follow those links, and you can start to explore the data the way we explore documents on the web. Now, and so we can actually build this into JSON. This is an example of something called JSON LD, JSON with linked data. And we can give it a context. And now instead of decontextualized name-value pairs, we have contextualized name-value pairs. So for example, this over here, saying my context is schema.org, tells me what name means. Unambiguously, globally. If I have title, it tells me what title means. Unambiguously, globally. We don't have to worry about, is it title like the title of a person, like Mr., title like nobility, like, Your Highness? Is it title like the title of a book? Is it title like, any of these variations? We know exactly what it is, exactly what it means. And we have types. And so essentially, with JSON LD, we're just adding links to the data. So we have a URI that represents this term name. We have a URI that represents this term birth date. A URI that represents this term birthplace. And just like if I don't know what this 6995 URI means, I can look it up and get information. If I don't know what that term means, I can look it up and get information. And not only that, a standards compliant tool or library, if it doesn't know what that term means, it can get that metadata. And now it understands it without us writing any custom code to recreate the semantics and the meaning and the behavior and the rules of the data. Because all of that can go with the data now, instead of just decontextualized name-value pairs. So essentially, each name-value pair has 3 parts instead of 2. It has, and each one of these, so because it's got 3 parts, it's called a triple, and each one becomes a single atomic fact about a subject. So we can look at this and say, Michael is from Wyoming. Michael's birthday is July 10th. So each one of these triples communicates a single fact. It's one cell in a database table. It's one line in a JSON doc. It's one edge on in a graph. And it breaks down to 3 parts. Michael is the subject of the statement. From is the relationship to the object. We call it the predicate. From is the predicate, and Wyoming is the object. Subject, predicate, object. Michael is from Wyoming. And as a result, we have a link, a URI that represents Michael, a URI that represents this relationship, and a URI that represents the place, Wyoming. In this case, it's a URI that comes from a project called DBpedia, which we'll talk about in a little bit. Links give us the extra information. They provide semantics. They remove ambiguity. They provide standardization, which means now I don't have to look at documentation or source code to be able to work with this data and recreate by hand coding all of the rules that only exist in the application code. All of that can go with the data as you move it around. And so this is a way to serialize a single fact. This is one serialization format. JSON LD is another. But this is called N triples because it's basically a file that is a dump of N triples. You have 5 statements, you have 5 triples. You have 500 statements, you have 500 triples. Subject with a URI, predicate with a URI, object. This one happens to be a string literal or a date. The little angle brackets specify that this is a URI. Quotes specify it's a literal. Now, it could get a little tedious to type out URIs over and over and over and over and over again. So another format is called the terse RDF triple language. And we can define some prefixes. So we say schema is the schema.org vocabulary. DBpedia is the DBpedia, is the terms and the resources in the DBpedia namespace. And so now I can say, yeah, w3id.org/people/Michael is a person with a schema birth date of July 10th and a schema birthplace of DBpedia, Wyoming. And there's a lot of these, RDF XML, RDF star, JSON LD, a lot of ways to represent this. And this is something called the resource description framework. If our documents on the web were originally resources and images on the web were originally resources, and then one of the early architects of the web, Dr. Roy Fielding, wrote his dissertation and derived REST, where any information resource on the web is a resource with a URI to identify it, and any non-information resource like me can be on the web with a URI to identify it. Like that w3id.org/people/Michael, that's me. That means me. And so anytime you use that in a statement about me, you're expressing a fact about me. And a really interesting thing that Neil talked about this big change when he talked about this holism problem, because there's always more to know. Well, they saw this coming in the 1990s, and they said there's always going to be more to know. So RDF was designed to accumulate information. It was designed following something called the open world assumption, that if you don't know something about, if you're not expressing something about a subject, it doesn't make it false. And there's always more that you can learn. There's always more that can be known. And RDF just effortlessly accumulates new information, new facts, which means if you're integrating data across silos, they just snap together without writing any custom code, without any of the stuff that we do over and over and over again. And essentially every fact in RDF is a fragment of a graph, and it's very, very easy to connect them. If I have a fact in one data set and a fact in another data set, I can just connect them. And we can represent any data of any shape and any syntax and any structure, and this builds on top of the web, the architecture of the web, which means it can scale like the web, which means it inherits all the properties of the web. And this was always the idea, that we wouldn't just have documents, we'd have data. And what if we had both at the same time? So this is my website. This is magician.codes. It's my charmingly anachronistic 90s style website. This is what a human sees. Now, there's a lot of human-focused information in here. But the vision of Tim Berners-Lee and the World Wide Web Consortium was to express the underlying data in the same document. So a human could look at it, get meaning. A machine can look at it and get meaning without having to do $500 million of compute to train a model on it. We can just pull the data out. And not only that, have explainable reasoning and explainable inference. Because when you ask ChatGPT and it either gives you an answer or makes something up, you have no idea. You have no idea where that came from. But when you ask data using these standards, how did you come to that conclusion? Because you inferred a new fact that wasn't in the data set. How did you come to that conclusion? And it will tell you. And it can explain all of its reasoning, all of its inference. But yeah, this sees. But if a machine looks at it, it's going to see a rich set of data. So let's look at the source of my website. So this is my website. And I can assign one of these properties to a span or a link, so it looks like this. So you can see in here, I'm saying the span property is name, and this anchor tag has a property of URL. And so if we look at this as turtle, we can see, Developer Summit is a schema education event with the schema URL of developersummit.com and a schema name of Great International Developer Summit 2023. This HTML shows the human the information, but also expresses the data as an RDF fragment. And you don't always have to express it. There's a lot of implied metadata here. Like if I look at this, I've got details of the event. And so none of this really gets shown to the user because it's clutter, but to a machine this might be useful. So I have the Indian Institute of Science as a schema place with an address, and this is what that graph looks like. So it's expressing information about the venue that we're in right now. And so if you actually look at the data that's embedded in my web page, you have a rich graph of information. And I'm only expanding a few of these nodes, but there's a ton of information in here. And anytime you want to learn more, you can follow the hyperlink to explore this broader graph of information. This is useful data. And if it sounds like I'm talking about the semantic web, I am. And the few people who remember the semantic web will say to me, wait, isn't the semantic web dead? Well, when we first heard about it, like Tim Berners-Lee's proposal, mostly nobody cared. But to quote the late, great Scatman John, while you're still sleeping, the saints are still weeping because those things that you call dead haven't yet had a chance to be born. And even though most people ignored the idea, few people saw the potential and saw the power and saw the vision. And like Neil Ford talked about, they wanted to work on something that would make the world a better place, that would leave a lasting impact. I can't imagine being an engineer with the realization that something I did made the entire world worse. Like we all want to make the world a better place. We all want to leave our mark. Nobody ever imagines that's going to be our mark. And like Neil said, it doesn't have to be. And these people said, I don't care if nobody else cares about this. It matters to me. Well, where's some information we can turn into data that becomes actionable? Wikipedia. It's all Creative Commons licensed. And so they started a project called DBpedia. And it was about 2006. They said, well, what if we took all the human-readable information in DBpedia and Wikipedia and turned it into one of these graph databases that we could connect to all these other things and build that graph of data? And they started decomposing Wikipedia. And in 2007, some other people saw the potential of this project, and they said, you know what? I'm going to volunteer to project my data into these same formats as well. And before we know it, we had this mesh of interlinked data sets that each made the rest of them more valuable. And that began the Linked Open Data Project. And within a few months, we got more data sets. And within a few months, we got more, and it got bigger, and go ahead. Well, it gets bigger. It gets bigger and bigger and bigger. This is what it looks like today. All right, take a picture now. I'll also, find me, I'll send you the slides. And the thing is, these data sets get integrated as fast as they come online. And this is just public data. And there's amazing things in here. All of these like red ones there in the corner with this really, really thick mesh of connections. This is biomedical data. And by connecting all these insights, researchers are able to find cures for diseases faster. They're able to come up with new drugs and treatments faster because all of this. And I saw a tweet a while back. Somebody says, y'all say the semantic web is dead, but I see you there surfing on Google's knowledge graph. Knowledge graphs. Google's widely credited with popularizing this term in 2012 because Google figured something out. Right, Google became successful in the late 1990s and the early 2000s because they had a slightly better ranking algorithm than anybody else. It was a little bit better. And in those days, that meant everything. But they figured it out that it doesn't matter how good your ranking is. It's an arms race. And not only that, Google has the best hits. Who goes to Google for hits? Nobody. We go to Google for answers. Conduit to the answer. So Google thought, well, what if we could just give them the answer? And they saw people working on these things and building vast graphs of knowledge. And they decided to buy one of these companies. They bought a company called MetaWeb to get something called Freebase, which was one of these knowledge graphs. And they could integrate it into Google. So when you typed in a search, it would give you your search results and your ads and all of the other garbage they give you today, and an answer. Like, that's probably what you're looking for, but just in case, here's some ads, here's some links. And this is how, when you type in certain things, like this is a nod to Brian Sletton, who really inspired me on this. Type in Fish concert, Google gives you the dates of the concerts, where they are, whether they've been rescheduled or not. And Google works this in their other products. So I can put linked data in an email, and if you're using Gmail, Google's going to pull that out. Like if I put linked data in your email, and it's about flight, Google's actually going to pull all this information out. Oh, here's your flight. It's on time. It's Terminal 1, Gate 12, and it's going to arrive in Zurich at 10:40. Here's the link to check in. Now, Google's not sitting there building custom integrations into every airline carrier's data information system. They're not going to do that. When you go to Google and type in hotel tonight, it's going to give you all the availability and rates. They're not trying to integrate with 10,000 hotels, with 10,000 different systems and 10,000 different APIs. They say, no, follow the standards or you don't show up. And it's changing everything. And because of this, people are saying, oh, I want my information to be in this graph. And they say, great, follow the standards or you don't show up. And now more than half of the indexed web has embedded JSON LD, and even more has the type that I'm using, which is RDFA, or microdata. And we're starting to reach a tipping point. And we're reaching the tipping point just in time, because there's a problem shift in technology. You know, I used to feel imposter syndrome over my Stack Overflow-driven development, but now I'm starting to realize the truth. We've shifted to working on harder and harder problems. And so much complexity gets abstracted away so that we can focus on these harder problems. And the hard problem today is data and integration and answers to questions that we never thought we'd need to ask. And the answers are scattered across dozens and dozens of enterprise silos. And we have no way to connect that without writing more and more and more custom code that recreates the semantics and recreates the business rules so we can actually start to connect this stuff. And we can't do it by hand anymore. 90% of the 2017 IBM Marketing Cloud said 90% of the data in the world has been created in just the last 2 years. 2.5 quintillion bytes of data a day, and it's growing much faster. It's driven by a bunch of key trends. You know, we're generating so much data from sensors and social media and new systems, and we're capturing more and more than ever in our data. And we have this problem. These two lines are not going to converge anytime soon. At one point, a study in the early 2000s, they estimated that the sum total of all human knowledge was going to be 11 exabytes. The IDC predicts that by 2025, the total amount of digital data created worldwide will rise to 163 zettabytes. Who knows how many zeros are in a zettabyte? I don't. I had to look it up. It's 163 sextillion bytes of data. How many zeros are in a sextillion? I don't know. I had to look it up. This many. So, and this is the wrong notation. I thought about changing this to the Indian notation, but I'm going to be honest, it confuses me just a little bit. And by a little bit, I mean a lot. So let's put it this way. Let's find a new system that we can all agree on. Who remembers the humble floppy disk? Okay, half of us. That makes me feel old. 3.5-inch floppy disk. So if we were to put 163 zettabytes of data onto floppy disks, we would need 110 quadrillion floppy disks. That's still too big to imagine. So put it this way, if I took those floppy disks and I laid them end to end, that would stretch 5.8 trillion miles. That would be a light year. The distance that it takes light to travel in a year is how long the light from the sun would take to get from one end of those floppy disks to the other. And anybody who's ever actually used floppy disks and you're trying to reinstall this, you know you're going to get to like, floppy disk 0.2 quadrillion, and it's going to be corrupt and your whole install is going to fail. Yeah, still too soon. So we've got all this data, but where is it? It's 1989 all over again, scattered across countless information silos. It means you have a new business question to answer. You got to start to integrate stuff. It means you connect into a custom app with its own custom server, hosting its own custom information system with its own commands and quirks and its own method of organizing information. You need to look somewhere else, start all over again by reading the API docs. And every time we need a new capability, we need to be able to answer a new set of questions, we build another information silo. And we do all of the work to recreate and recode what should be traveling with the data to begin with. And, as Tim Berners-Lee says, there's always going to be a number of information management systems, and we get a lot of usefulness being able to cross-link them, but we're going to lose out if we try to constrain them. We still need information systems. We're always going to need information systems. But should those applications hoard all of the data and hoard all the business logic and hoard all the business rules and hard code into code that is compiled and hard to work with? So the solutions to the upcoming problems aren't going to be solved just by creating more silos and hard coding the business rules and the semantics again and again and again. The business, we need to be able to move a lot faster. We need to be a lot more agile. And we're seeing really interesting things happen. We're seeing interesting things happen in the around the enterprise knowledge graph, because we did this. We went through this journey a little while ago, and because we've been having these problems for years, and we say, well, what's the alternative? Is it yet another application silo? That hasn't been working. That's not scaling at the rate that we needed to scale to keep up. And then somewhere in the 90s, we had this idea of, what about this? One silo to rule them all. We'll have an enterprise data warehouse. And there's a lot of challenges with this. One of the biggest challenges is that we don't all see the world the same. And we have different perspectives. And data means different things in different contexts. But with a data warehouse, we have to all agree on one context. And something really interesting happens when you try to do that. When you try to find the lowest common denominator, the average. There was a study they did years ago where they were trying to figure out how to fit a cockpit to a pilot in a plane. And so they got all the pilots in the program and they measured them. And then they took the average. And it meant that the cockpit didn't fit anybody. Can you imagine if the clothes that we wear, they just measured everybody, and then they picked an average, and they say, okay, here's the average size t-shirt, there you go. It's going to be horrible on everyone. We need different sizes. Sometimes we need tailored clothes, and that's how I can come here and look as dapper as I do. And so this failed for a lot of reasons, but the consensus-driven approach was one of them. The data lakes had fewer rules and fewer constraints, and they gave us a larger view of our data, but the integration remained brittle and messy, and it still requires a lot of custom coding. And we hide the integration challenges, and we hide some of these things, but we can make this stuff more turnkey and more agile. Where was I? And so this is what the enterprise knowledge graph is doing. It's allowing us to keep the data everywhere, wherever it happens to be, and be able to connect it and being able to look at it in all these different contexts. Look at it in the in the, and you could look at the world through your lens and your context and your rules and your perspective and your ethos. And having this information connected across the enterprise is allowing the enterprises to answer these questions. Because there are pressing business problems right now in almost every organization we're affiliated with that we could solve if we were able to link and query the existing data. But what we do is we realize that there's too much cost associated with that right now. Right, 35 to 65% of an IT's budget is just integration. And so often, business will look at this and say, yeah, we can spin up a team of developers to build another information system or to set up Databricks or Snowflake or whatever else to try to come up with this new view of the data, but that's going to take too long. The opportunity cost is too high, so we're just going to hire a bunch of people to look at it and collate and customize and write reports because I can throw 100 bodies at this and get an answer faster than a team of developers. Now, the team of developers is more scalable, more reusable, but sometimes you can't even wait for the opportunity cost. And the challenges of IT in the future are all about reducing the cost of compute, whether it's wall clock time, whether it's energy time, whether it's CPU time, whether it's opportunity cost, reducing these costs. And the technologies that are enabling that are the most interesting and going to be the most influential in the future. And so to get here, because this is a hard place to get to, and that's why, there are a lot of companies that are using knowledge graphs and using linked data. And this slide is 4 or 5 years old now, 5 years old now. But we can start looking into and investing ideas that are stepping stone technologies. And one stepping stone is adopting the ideas from the data-centric manifesto. And the data-centric manifesto, people say that data today is trapped in enterprise applications and web platforms, and until we realize and take action on the core problem, the situation is going to continue to deteriorate. They say, we believe that the current enterprise information system paradigm centered on applications with data as second-class citizens is at the heart of most of the problems with current enterprise systems. We further believe that the main barrier to changing this paradigm is not technical, it's mental and inertial. And we can be that change. We understand there's a huge amount of money to be made in building and implementing and integrating applications and organizations, and that's what keeps the application-centric paradigm alive. Just like with Neil talked about, there's a lot of money doing evil things. But we believe there's even more money to be saved in the enterprises that produce and consume information by moving to a data-centric approach. So linked data powers data-centric. Data-centric powers knowledge graphs. They're stepping stones, and each step along the way enables amazing capabilities. It takes concerted effort to change entrenched habits, especially when there are large financial incentives to do so. Therefore, we commit ourselves to begin the process that will lead to a data-centric architecture in the firms we work with. There are principles. Data is the key asset of a firm, person, or organization or society. Our data is our asset, but we give it to the companies so we can get a website for free. We can flip the script, and linked data powers that. There's a lot more down this rabbit hole. Data is self-describing and doesn't rely on applications for interpretation and meaning. This we can do today. We've been doing this for years. This is how the linked data open data project works. The data is self-describing, and it doesn't rely on applications to give it interpretation and meaning. It's expressed in open, non-proprietary formats. There's a lot of great standards around this: JSON LD, Turtle, RDF, and Triple. And these are the core ideas, that the data can kind of live independently from the application. And that's kind of what this purple thing in the middle is. It's not like a data lake or anything like that. It's the data as a concept that is independent of the applications and the structures. And, we can make these changes. The future has a reasonable cost of change. Data is an open resource that outlives any given application. Every new project can tap into existing data stores the same way the linked data project gets more powerful every time we connect a new data set. Data integration will be nearly free rather than 35 to 65% of the budget, and internal and external data can be readily integrated. And so all of the stuff that started with the semantic web and moved into this graph space and data-centric, all of this is making this possible. We have an amazing technology stack. So going back to REST, we have the resource abstraction. I talked a lot about that yesterday. We have RDF, the resource description framework, which now gives us that metadata. We have RDFS, which is a schema language, which starts to create some powerful capabilities. We have OWL, which is the web ontology language, which allows us to formally describe what we know and empower axiomatic reasoning and inference in our data set, the same way that we reason. We have Sparkle, which is the Sparkle protocol and RDF query language, which allows us to get the data out, ask questions, reshape it dynamically to meet our needs. We have Shackle and Spin that allow us to control the data and apply all the business rules that we normally express as code as part of the data, just little more data. They're just more triples. And we have RDF star, which allows us to make statements about statements. And so it's not hard to start moving this direction. The first steps to link data are, we do it incrementally. We stay with our preferred technologies. We just start thinking about the linked data principles. The linked data principles are we use URIs as names for things rather than ambiguous, meaningless keys. We use HTTP URIs because there are other types of URIs, but the HTTP ones are resolvable, which means people could look up the names. They can explore this information space. And then when somebody looks up a URI, provide useful information. And that means follow the RDF standards. If you're giving JSON, it is trivial to turn that into JSON LD. And you don't even have to edit your JSON at all. You can turn JSON into JSON LD with 0 edits. That's amazing. And include links to other URIs to facilitate finding more data. And so this means that if you're building APIs, use stable, resolvable identifiers, and use level 1 or level 2 APIs on the Richardson maturity model. Take some time to understand some of the details of some of the more subtle details of REST. It's not just RPC over HTTP. It's an architecture that enables amazing capabilities. And I'm going to leave you with this, because I believe we are on the cusp of what I'm going to call the next Fosbury flop moment. And I'm going to explain that. Because the problems we need to solve with software are increasing complexity. And our software needs to drive interdisciplinary and interdomain insights in ways that we can't anticipate. And the application of the ideas are allowing companies to out-innovate their competitors, and soon you won't be able to be competitive without them. That's what I mean by Fosbury flop. You see, in 1962, a young, awkward, not very athletic, very unremarkable young man named Dick Fosbury decided he wanted to participate in high school sports. They don't have cricket in America, really, in the schools, so that was out. Same with football, American football, but he was too scrawny to play American football. And he finally joined, he was too short to play basketball. He finally joined the athletics team, track and field. And he wasn't a fast runner, and his coach said, well, you can do the high jump. And this is how they used to do the high jump. They would jump and straddle the bar. And he couldn't even clear a 1.5 meter bar. Couldn't even get this high. And that's not even competitive in a school. So he developed his own jump technique. And it was weird. It looked silly. And everybody just kind of laughed at him. Until he shattered the school record, and that technique was the Fosbury flop. School record. Nobody had ever jumped that high before. In 1965, he took it to university. And again, shattered the university record. In 1968, he went to the Olympics and set a new Olympic record. He jumped 2.24 meters. Nobody had ever jumped that high. And in that moment, the game was forever changed. If you weren't jumping using the Fosbury flop, you couldn't be competitive in that sport. And this is still the technique we use today. But we've seen this kind of disruption before. Assembly line was the same sort of thing. Henry Ford popularized the assembly line with the Model T, and it was a game-changing moment. And after that, you couldn't be competitive in manufacturing on any meaningful scale if you weren't using the assembly line. You couldn't cling to the old ways and still be competitive. It was obsolete. Digital computers, the same thing. It happened in the 1960s. You couldn't be competitive. In the 1980s with personal computers, you couldn't be competitive. And there was a point in the 1990s where you couldn't be competitive unless your business was on the web. And today, we're seeing this in the 2020s with linked data, knowledge graphs, knowledge systems, and everything that all of this empowers. It is a very cool space, and it's an opportunity to work on something that has the power to change not only our organizations, but change the world. Thank you.